How's it going, everybody? Welcome to the second drill here. I want to start off today by mentioning a couple quick notes. First, I want to make sure to explicitly encourage everybody to take your own notes and comment things throughout scripts as you go through the videos and as you go through these scripts. Especially because this week and next week may feel like I'm throwing a lot of information at you, but just remember that it's there for your reference and for you to go back to, and that you don't necessarily need to memorize everything that I throw at you, over the next 2 weeks. And instead think of these scripts as references, and the things that we're going to be doing a lot of, like you'll pick up on those things and they'll become second nature. And especially because today we're going to be talking just about a few functions and some base R stuff, and that distinction between base R and tidyverse, I'll make it much more clear next week when we get into the tidyverse. Basically, there are ways of doing things that are just the default built-in functions that R has without any external packages and that sort of thing, and that's this base R method. Now, once we get to tidyverse next week, we are for the most part going to leave base R behind, and there will be times that base R type references have to be used because of old functions that just don't play well with tidyverse and things like that. And also, whenever you're just looking on help for Stack Exchange or whatever, you'll see base R notation sometimes, and so you need to be able to recognize that and interpret that. So it is important to at least be familiar with base R, but next week's functions are going to be a lot more important for how we're going to be doing things, at least as far as the stuff dealing with manipulating data and like subsetting and selecting certain things and things like that. So I just want to throw that out there from the beginning, because that's one of the things that we're going to talk about today. This other note here is that what I try to do as I'm teaching these courses is not just tell you what to do or how to do it as far as here's how you do this analysis, but rather I really want to explain the why behind things, because if you don't understand the why about something, then you're not going to know when a context changes and the way that you learned doesn't directly apply anymore, and there's some sort of tweak that needs to be made. In other words, every research design, analysis plan, data set, whatever, you're invariably going to run into differences and problems, and like that's one of the headaches, is figuring out how to kind of do that next thing. But when you understand the whys behind some of these things that we do, when you get to some situation where you can recognize, like, wait a second, this context is a little bit different than the context that we learned it, but so I need to do it this way instead because this is why it was done this way, and that why has now changed. So I need to figure out what's different and how I need to approach it in a different kind of way. So in other words, it's never going to be data science, and data analytics is always about problem solving. I talk about one of the reasons that I love this is because it's kind of like a puzzle, but it's a puzzle that you don't necessarily know what the finished product is supposed to look like. You just have all of these pieces. And so especially with R, where you're doing it all programmatically and really from the ground up, you may not even have all the pieces. You might need to borrow some puzzle pieces from someone else's puzzle. So you get online and find where somebody else has a similar puzzle and they did something. So you take one of their puzzle pieces, but maybe the color of it isn't exactly right. So you take their puzzle piece, but you got to modify their puzzle piece a little bit, and you got to paint it a different color, or maybe trim off some specific edge to tailor it to your specific, where you're trying to fit it into your puzzle. But at the end of the day, data science and data analytics mathematics. It's basically a big puzzle. And so understanding why certain pieces fit together or have to fit together or can't fit together, certain ways, will help you adapt to differences in the future, whether it's running into some problem with messy data or just a different design than what you're used to, anything like that. So just know that a lot of the explanations that I'm trying to give on the whys behind things is so that you can really understand what R is doing or what your analysis is doing theoretically, so that you can expand and adapt from there. That being said, I sometimes, to explain the why we do something a certain way, it either has 6 other things that I have to explain to get to the actual reason why. And so sometimes I will just say, like, hey, just trust me on this, take a leap of faith, and later down the road it'll make sense why I told you to do this way. Some other times that there will be, I don't know if you've heard of the trope or expression lie to children, which is to explain something, a technical thing, to the lay person or to a non-expert in a way that isn't technically factually correct 100%, and so kind of fudging the truth a little bit to get someone thinking in the right direction, and then later on the full truth can be revealed and will make sense, having now learned that little lie first. And so sometimes I lie to children, but I typically will tell you when I'm doing that, kind of like last week how I said names can't begin with numbers, and then almost immediately told you, well, that's a lie, but I'll explain why later. It'll be next week when we get to Tidyverse that I will finally explain why that was a lie. In general, you shouldn't, just to be clear, you shouldn't name things with numbers. I'm just saying it's possible and you can if you're using Tidyverse. But I digress. So I just wanted to throw that out there. And like I said, I'll let you know whenever there's something that, that I'm not exactly being technically correct about it, but it's the approximation that you need to know for now. And then that said, as always, if you ever have any questions or you want to know more about why, or if I forgot to mention the why about something and you're just like, well, why are we doing it this way? By all means, just ask, and I'll be more than happy to explain, the reasons why, or point you to the resources that explain those things. So that said, let's get into today's script. And first we're going to talk about data types and structures. And this is important because we'll be talking about different data types here today. For now, I'm only going to talk about the 4 types that we need to know for now, which are character, numeric, integer, and Boolean. So the character is exactly what it sounds like. It's any sort of character string. So here we have a character string. It's just this M, and you can tell it's a character string, so it's in quotation marks. And so this is just a one string, or a character string with one element. And this is another character string that has 4 characters. Numbers, real numbers, or numbers with decimals. Integers, exactly what they sound like. They are the integers. I will say that if you have an integer in your environment, it shows up with an L, and that's how R identifies things as an integer. So if I just save like the integer 5 as a thing called A, over here in my environment, you can see that A has the value of 5L. That's saying the integer 5. Factors, and Booleans. So a Boolean is just the true or false. Mathematically, that's represented as 1 and 0 respectively. False will be 0 and trues will be 1 if you're converting Boolean to numbers. Factors, for now, I'm just going to say that they're nominally different. There is some more information to it, but we'll talk about it when we get there. For now, just think of factors and characters, or character variables, as more or less the same thing. But what kind of data it is only half the story, and the other half of the story is its structure. So its structure is defined by its dimensionality and its homogeneity. So a one-dimension data structure only has the one dimension is its length. So, think of it like a row, and it can have one element, a length 1, and it's just one number. Or it could be a length 10, and it's, 10 numbers, but length is the only dimension. A two-dimensional will have a length and a width, or height, or whatever you want to call it, but it's basically a table. So if you think of something that has 5 rows and 10 columns, we now have 2 dimensions. It is a 5 by 10 data structure, and so we have that second dimension. And for homogeneity, it's just what in those things, whether it's a single row or a table, is it all the same type of data, or is it different types of data? So if it is all numeric, then you have a homogeneous data set. If you have like one column that's numeric, another column that's character or whatever, then you have a heterogeneous mixture of data. So if you have a one-dimension data set that has homogeneous data, so it's just one type, then you're looking at an atomic vector, or just a vector as we'll refer to it as. So a numeric vector if it's all numeric data, a character vector if you have characters in it, etc. A two-dimensional data structure that is all homogeneous, so it's all the same, is a matrix. So if you have 5 columns and 5 rows, but all of the values in that table are numbers, then you have a numeric matrix. If it's characters, you have a character matrix, etc. So a matrix means that everything in there is all one data type. And then if you have a two-dimensional structure that is mixed, that's where you have a data frame or tibble. And tibble is just the tidyverse data frame, so we'll talk about it tomorrow, next week, as far as what the tibble is and the difference between the data frame and the tibble. But all you need to know is that a tibble is a data frame. It's just a data frame that has some extra nice features, but we'll talk about it next week. But throughout today, just so that you don't get stuck in your head data frame and then get confused when I say start talking about tibbles, from now on, beginning next week, from next week on, then you won't be confused. But that data frame or tibble is going to be your two-dimensional data set that has heterogeneous types. So you might have some characters, some numeric, some integers, whatever, it can be mixed. And then the one-dimensional mixed data structure is a list, but I'm not going to talk about those because we won't be dealing with them for a while. But that said, let's hone in on some basic functions. I said last week that functions are just these things that you give it some input called arguments, and it does some stuff. It normally gives you an output, whether it's down in the console, over in the plots or the viewer pane. Sometimes it will write stuff. So if you're writing a CSV or writing a PNG graphic to export a plot that you made or whatever, so it does stuff based on that input, those arguments that you give it. So we're going to look at a few basic functions today. And to start, I wanted to point out that if you can get R to give you a sequence of consecutive integers just by putting like the first and last number that you want separated by a colon, and it will give you that sequence of integers. So 1 colon 10, if I run this line here, it will return all of the integers 1 through 10. Here 4 colon 9, that returns the integers 4 through 9. But sometimes you need more flexibility in a sequence than I need consecutive integers, and so the sequence function seq parentheses will give you that flexibility. So look at the help file. As I mentioned last week, throw a question mark in front of it, but this week I wanted to kind of talk a little bit more about what all is contained in this help file. So you'll see the description up at the top. This usage here we'll come back to. It will define what each of the arguments in the usage, what each of these arguments actually mean. And then there will typically be some details and some examples and things like that, and also some links to related things or dependencies, all sorts of stuff like that. So the most important thing, though, where you're going to be looking most often is in this usage and in the arguments, and to a lesser extent in the details. But there's some important information here, namely that it has the so if we look at our sequence function here, this tells us what our possible arguments are: from, to, by, length out, and along with. And that also tells us the default order of those functions: from, to, by, length out, and along with. And there are also a few that have default values in this. So where it says from equals 1, to equals 1, that means that the default value of from is 1, and the default value of to is 1. We'll talk about exactly what that means in just a second. So once we look there, you can look down and see here what each of those arguments mean, but we'll discuss it. So if we say sequence, parentheses, from equals 4, to equals 10, by equals 1/2, each separated by commas, if we run that, it's going to give us a sequence from 4 to 10, increasing by increments of positive 1/2. Now, because the default order of these arguments over in our documentation are from, to, and by, that means that if you just put in any three numbers, R will assume, if you don't specify from equals, to equals, and by equals, R will assume that that's what you mean, that the first number that you put into the function is from, and the second number that you put into the function is to, and the next number that you put into the function is by. So if we run this sequence or seek 4, 6, 1/2, then it will give us that sequence from 4 to 6 increasing by positive 1/2 increments. So you don't have to use the explicit arguments if they are in the order of the default arguments, but flipping those around won't work. So here, if I try to run sequence 6, 4, 0.5, it's going to tell me, you can't do that. There's an error here, and that's because it thinks that I just told R a sequence from 1 to 4 by 1/2, and it's saying you can't get from 6 to 4 by increments of positive 1/2. If I wanted to make that a negative and run it, it could do a sequence from 6 to 4 by increments of negative 1/2. But my point is that if you are entering things in the order of their defaults, then you don't have to use those explicit arguments. And if you use the explicit arguments, so here we have 2, 6, from 4, by 1/2, and it'll run, or by 1/2, 2, 6, from 4, we'll get the same thing. So when you use the explicit arguments, it doesn't matter what order you put them in. And so most of the time you should use the explicit arguments. One, it takes away ambiguity in your code, so it's just a good coding habit. And another thing that you'll see very soon is that a lot of functions have a lot of possible arguments, and we'll often only put in 1 or 2 specific arguments, and so you have to use the explicit ones to tell the function which argument you're putting in anyway. So it's just not a bad idea to get in that habit. And then finally, so instead of giving it like a specific starting point and ending point and how many increments you want it to go up by, you can use this length out argument to say I want to increase by increments of 0.382 30 times. Now, one thing to notice here is that I don't have a from argument, but that's what earlier when I said that it has a default of from equals 1. So if you leave from off of this function, it will put the number 1 in for you. If you leave off the 2 and you're doing something that needs the 2 argument, it will put that 2. So here, if I just say by 0.382 length out equals 30, then what you'll see is by default it starts from 1 and goes up by increments of 0.382 30 times to whatever that ending point is. If I say sequence from, or if I leave the from or to blank, and I say from equals 0 by equals 0.1, then that 2 automatically defaults to 1. So R actually reads this as from 0 to 1 by 0.1 because, again, those default values are 1. And if you leave them out, R will put 1 in their place. Often you'll see null here for additional arguments that aren't run typically. And so if you see null, then by default that doesn't need an argument. But again, R will put in whatever these defaults are if you leave them out. So we talked a little bit last week about storing things as objects. So we could store, one of these sequences as an object. So we have this from 4 to 10 by 1/2, and I'm going to store it as an object called 4 to 10 here. And now we can see over in our environment, we have a object called 4 to 10, and it is a numeric vector that has 13 elements, or a length 13. And if we come here and then run this line, this command 4 to 10, it will display it in our console, and we can see that sequence that we stored. But what about if we need to store, non-sequential numbers? So here, if I just try to store 8675309 as non-seq nums, it's going to throw up this error and say there was an unexpected comma, and that's because it tried to read right here and store 8 as non-seq nums, because then this comma, it doesn't know what's supposed to come after that. In order to combine stuff or concatenate stuff, you have to use, there's a function that is this C parentheses, which this tells R things inside this parentheses go together as one vector. And it's important to remember when I say that it puts it together as one vector, because if you recall, earlier I said a vector is necessarily a homogeneous data type. So we'll see why that's important here in just a second. But so instead I have the same thing here, but I just wrap 8675309 in C with parentheses, and now you can see that it's stored that non-seq nums as a numeric vector. We can use the structure function str to look at the type, structure, and dimensions of an object. So if we run structure on non-seq nums, we can see that it's a numeric vector, that a vector because it only has one row here, and it has length 7. We can see that same thing over here in the environment, quick note that sometimes you'll see R telling you that something is double or DBL instead of numeric or NUM. And all you need to know is it is literally 100% exactly, and I mean that in the scientific sense, numeric is double. And why they're named two separate things, I'm not going to get into. You don't need to know. All you need to know is that if you ever see double, it's numeric. Double and numeric are one and the same. You can coerce R to make data into other types of data should you need to, and sometimes you will need to because certain arguments require certain data types. So even if it's if you have integers in there, but whatever function from whatever package is expecting numeric data, it's going to throw an error and say, we can't do this, something's wrong here. But if you change it instead from numeric to, or from integer to numeric, then run it, it'll run just fine. So you can do that with this as dot type function. So as dot integer, for instance, we can take this non-seq nums, which again is 8675309, the numeric vector, and if we wrap that in as integer, and I'm going to store that as an object called ints, and now we can see we have this object called ints down in our environment, and we can look and see what that is. And when we look at our structure, we see that indeed it is an integer vector now. It's not a numeric vector. We can make that, if we wrap it in as character, we can make this into a character vector. So here, even though it looks like the numbers 8675309, you'll notice that it has those quotation marks around it, which is how you know that it's actually, that those are characters. And so, yes, they look like the visual representations that we recognize as numbers, but R recognizes those as characters. And so this is important because, for instance, with our non-seq nums, you can do arithmetic on a numeric vector. And so if we run this line, it will add 2 to each of the values in that vector. But here, if we try to add 2 to this cars object that we created, it's going to say you can't do that because you can't do math with characters. Like, it has to be, numbers. But you can concatenate or combine character strings as well. So here we have this, the string of 7 names, and it's wrapped in that C parentheses. And so when we run that, we now have a character vector called West Wing that has 7 strings in it. And when we check our structure, again, we can see a character vector, and it has 7 elements, strings inside. But what's going to happen if you use concatenate or combine two things that were already concatenated? So say we have our West Wing object here, and our non-seq nums object here. So if we try to combine these two things with this concatenate, so I'm going to run that and store it as a thing called combined vectors and take a look at it, and you see that it's a character vector that is length 14. So it took that numeric vector and it made it into a character vector and then combined both of those vectors into one big long vector. Well, if you remember up here, I said that concatenate combines different things into a vector, and then up here I said that a vector is a homogeneous data type. So those two things combined, what that tells you is that this is called implicit coercion, where R is kind of under the hood changing the data type. It's coercing those numbers into characters, because you can make numbers into characters, but you can't make the letter, like the word Jed, into a number, or the word Leo into a number. So you can't go the other way with this coercion. So you kind of downgrade the number down into a character so that everything becomes that same data type. But so what if you wanted to make this into, instead of one long vector, you were trying to stack it to make it into either 2 rows on top of each other or 2 columns side by side? That's when we would use, or one possibility is R-bind or C-bind, which is row bind and column bind. So if we run R-bind with non-seq nums and West Wings, what we're doing is we're telling it, take these 2 vectors, but make them into rows and then combine them together one on top of the other. So when we run this command, that's what we'll see. It takes that non-seq nums and makes it a row and then puts that on top of the West Wing vector. And so now we have this output. The C-bind does the same thing, but it makes it into columns. And so it will take that first object, make it into a column, and then take that second object and make it into a column and bind them together. But I'm going to C-bind those, but notice that again, we don't have anything new down here in our environment because I made this, but it just outputs in the console. I didn't store it as a new object, which is what actually puts it in our environment and makes it usable for later things. So I'll do that here by storing this C-bind into an object called ASDF, which is one of my frequent, just example one-off things that we don't really need. And then when we look at the structure of ASDF, we see that it's a character matrix that has, and we can also click on it over here, and we can see that it has the 2 columns with 7 rows. And we can see that here we have 7 rows, 2 columns, and this character matrix. Well, again, our numbers have been turned into characters, and that can be a real problem. So once again, that's because the output of cbind and rbind is a matrix, which is necessarily homogeneous data type. So R will implicitly coerce whatever data you put into it into the lowest data type. So in this case, it's going to make it characters. If you're wanting to keep those numbers as numbers, then you have to put them as a data frame or tibble. Remember that that's the only way a two-dimensional data structure that is heterogeneous is a data table or tibble, or data frame or tibble. And so here I'm going to take those same things that we did in the cbind, but instead I'm going to use this data frame command. And I'm going to store that as an object called data frame 1, and when we take a look at it, we can see that it just named the columns, named the variables, what our vector names were. But when we look at our structure, we see that it is now a data frame, not a matrix, and there's 7 observations, which means 7 rows of 2 variables or 2 columns. The first column's name is non-seq nums, and it is a numeric column, and here are its values. Second column is west.wing. It's a character variable, and here are the first few values. But I don't like those column names. Those would not be fun to have to type out, and they might not make the most sense. So instead, I'm going to change it, and I'm going to say same thing as this, but I'm just entering this num equals non-seq nums, and car.name equals west.wing. I'm going to run that and save that as an object called df2, which you can see is now down here in our data set. And we can click on it down here to look at it in the viewer. And we can now see that that first column is now labeled num, which is what we told it to name it. And then that second column is named car name. And if we look at our structure, again, we see the same thing, that it's a data frame, 7 observations of 2 variables. The first column is called num. It's a numeric variable. Here are some of the values, and then car name is a character variable, and here are some of the values. So now that we have this very small, simple data set, data frame, df2, we're going to look at indexing and subsetting. So there are times that you'll need to call a specific element or some specific elements, or subset specific rows, columns, whatever the case may be. So if we start by looking at just the west wing object here, which just as a reminder is this character vector. When you use brackets, or we use brackets for subsetting, and when you have a vector like this, the way that it works is, if we put a 1 in this bracket, it's going to call the first item in that vector. So it's just going to return Jed. If we have the 2:4, remember that this notation means 2, 3, 4. It's like all 2 through 4 and all the integers in between. And so if we put that inside the brackets, it'll return the second, third, and fourth values. Then here, if we need, again, the non-consecutive values, then we use that concatenate function. And so if we say west wing, and then in brackets, the C parentheses 1, 4, 5, this will return the first, fourth, and fifth elements, or Jed, Toby, and CJ. If you're indexing a data frame, matrix, tibble, etc., where there's 2 dimensions, then inside your brackets there are also 2 dimensions, and those dimensions are row, comma, column, and that's always the case. It is always row, comma, column. So df1, 3 means from this data frame, whatever value is the first row, third column. If you leave something blank, that means all of whatever. So in this case, where it's like from this data frame blank rows, that means all rows of column 3. So that would return the entire third column of this df. So for instance, if we look again at what df2 is, like this is that data frame that we're talking about. So if we look at 5, 1, that means the 5th row, first column. So if we look in this first column, 5th row, that's a 3. So this line should return a 3, and it does. Here we're looking at the third row, second column. So the third row of the second column is Josh. And sure enough, that's what it returns. And then once again, if you leave that blank, that means all of something. So this means all of the rows in the first column, or on row 3, all of the columns. So you can see that it runs that returns the entire row 3. Now, columns can also be indexed by their column names. And so we could say rows 3 through 5 of the column named car name, and it's going to return those values for us. And we could say columns or rows 1 through 5 from the column named num, and it'll return those first 5 numbers. And then again, you can, if we leave the rows blank and just put in a column name after that comma, so bracket, leave it blank, and just put in a comma and then the name num, it'll return all of the rows in the num column. Or df2 bracket comma car name will, since rows are blank, it returns all rows of the car name column, and so it'll return all of those values. And then this, there's an easier way to do this here in base R, which is with these $signs. So if you're trying to return an entire column, then all you need to do is write the data frame name, a $sign, and the variable that you're looking for. So df2 $num will return the numbers. So that's the same as this, but a lot easier to type. And then df2 $car name will return that entire car name column, that variable. And so then finally, you can also include logic in these indexing brackets. So if we say from data frame 2, and then in brackets we want to index a specific thing, and that specific thing is we want all columns because that's blank. But then for the rows that we want rows where df2 $num, so in other words where this column where that value is greater than 6. So this says from df2, from the data frame df2, select all of the rows where num is greater than 6 and all of the columns. And so if we run this line, it will return these three variables here, where we have num is greater than 6 and it will return all the columns. Now, if it feels like I kind of blew over this stuff pretty quickly, that's because this is by and large the base R stuff. There is a much better way to subset and to slice up all of this data. And that's what we're going to do next week. And so we'll basically, for the most part, we'll be leaving a lot of this behind. We do still use the $sign notation some, and we still do use some bracket notations here and there. But as far as like to call specific things and whatnot, like there's the tidyverse data wrangling stuff is going to be a lot easier. So again, I'm just trying to briefly introduce you to it so that at least when you see it online, you recognize what it is and you're not like, wait a second, this is nothing like anything that I learned. So going to look at a few other functions. If you want to look at the first few values of something, whether it's a vector or a data frame, whatever, there's a function called head. It defaults to showing you the first 6 things of whatever things those may be. So if we look at this combined vectors, the whole thing is this 14 length 14 character vector. So if we look at head combined vectors, it's going to show us the first 6 items in that vector. You can change the argument and say, head combined vectors, comma, n equals 11, and that tells us we want to see the first 11 items in this thing. But since n equals is the default second argument, you can actually leave that off and just say head combine dot vectors comma 11 and run that, and it's going to give us the same thing. If you have a data frame, then instead of just the actual numbers in the row, the number, it will tell R how many observations you want, and observations being rows. So head df2 comma 3 tells R I want to see the first 3 rows of df2. So if we run that, sure enough, that's what we get. And then tail just does the opposite and says I want to see the last 3 rows of df2. There are some summary statistics functions that are exactly what you'd expect them to be. If we look at our 4 to 10 object, which is that numeric vector from 4 to 10 by increments of 1/2. If we look at the mean, it's going to tell us 7. If we look at the median, it's going to tell us 7. We can look at the standard deviation, the variance, the length is how many items are in that vector, and we have 13. We can sum up all the items in that vector. And then there's another function round, and if I wanted to pull up the documentation here to point out that again, if we look at the documentation here, we see that there are 2 arguments that go into round. X, which is just some input, whether that's a single value or a vector or whatever you're putting in is X, and then digits equals 0 is the default. Well, digits is the argument that says how many decimal places to round off. So if we don't put anything in here, then again R will put digits equals 0 implicitly in there when it runs, and so this will tell it to round it with 0 decimal places, or in other words, round it to the nearest whole number. But if we tell it 5.7862 comma 1, then it will round to 1 decimal place. If we put in 2, it'll be 2 decimal places. 3 will be 3 decimal places, etc. And often we will be nesting functions within other functions, which is something that you can do. And so you've heard me say a few different times today something about wrapping something in some function. And so what that means is to like if you remember, we had this weird sequence, and let's just say that we wanted to round that. We could wrap this sequence in round, and then when we run this line, it will round each value in that vector to 2 decimal places. And the reason it's called wrapping it in something is because it's literally, if you want to round this, you just come to the front, type round, come to the back side, and put comma 2 close parentheses, and you've now wrapped that function in round. So that wraps up all we're going to be really talking about today. We do need to install a couple packages before next week, and those will be tidyverse and PSYC. So you can either delete these pound signs and then run these lines and it will install, or one thing that I want to make sure that I explicitly point out, because I do it a lot, is that if you have a portion of a line highlighted and you run it, that only runs the selected portion. So in other words, if I say sum of non-seq nums, if I put a pound sign in front of it, if I try to run this line, it's not going to run because R doesn't recognize it. This is just a comment. But if I highlight that, now R just runs the highlighted portion, so when I run it, it actually runs, and it ignores anything else that's not highlighted here. Just to say that you can just highlight and run that. Once it's done installing, highlight and run that, or delete those and run the lines, and then put the pounds back so that you don't accidentally try to keep reinstalling it. But the tidyverse package will next week we will talk extensively about what it is, and start getting into how to use it. And the PSYC package also has a couple really nice, convenient, quick functions that we'll be using quite a bit. So we'll go ahead and install that one as well. And if you have any questions, feel free to shoot me an email, or I will see you all on Thursday or Friday.